Four light bulbs are connected in a circuit with a 24-volt battery as shown in this figure. So in part A, determine the average potential energy change of an electron as it moves from point Z, down here, up to point X. So the electric potential energy is equal to charge times electric potential. So if we're looking for the change in potential energy, we can just put a delta in front of the U and the V. So say the change in potential energy is equal to the charge of an electron, which is negative 1.6 times 10 to the negative 19 coulombs, times the change in voltage, which as the electron goes from point Z to point X, the voltage difference between those 2 points you can tell just by looking around this other branch of the circuit, and it is 24 volts. So multiply that by 24, and you get a potential energy change of negative 3.8 times 10 to the negative 18 joules. You could have also answered this in units of electron volts. Instead of putting in the charge of an electron for the Q, you could have just said the charge is negative E and multiply that by 24 volts to give you an answer of negative 24 electron volts. Either one of those answers would have been acceptable. And the second part of part A, indicate whether the electron gains or loses potential energy as it moves from point Z to point X. Since this came out to be a negative answer, that is a loss of energy. And that's also the case because as the electron flows through the battery, it gains energy, but as it's flowing through resistors in the light bulbs, it's losing energy. So you can just put the check next to loses energy. For part B, calculate the equivalent resistance of the circuit. So if you notice in this circuit, we have bulb A and bulb B are in parallel with each other, and then bulb C and bulb D are in parallel with each other, and then the whole AB combination is in series with the CD combination. So let's take it one step at a time. Let's look at A and B first. So because it's just two bulbs in parallel, we can use the shortcut formula, which is, so the resistance of A and B combined is equal to the product of those two resistors, RA times RB, divided by the sum of those two resistors, RA plus RB. And that's equal to 6 times 3 over 6 plus 3, or 18 divided by 9, which is 2 ohms. Then we can use a similar formula for the equivalent resistance of C and D combined. That's going to be RC times RD over RC plus RD, which is equal to 12 times 24 over 12 plus 24. And that is equal to 8 ohms. And then since RAB, the equivalent RAB is in series with the equivalent of RCD, we can just add those together. So the whole combination, the equivalent resistance of the entire circuit is 2 plus 8, or 10 ohms. For part C, calculate the magnitude of the current through point Y. So the current going through point Y is going to be the same as the current that flows through the bulb B, since those are in the same branch of the circuit. So this is where it may help you to draw one of those VIR charts. So I'm going to put one down here. And just to make sure everything's on here, we have bulbs A, B, C, and D, and the last row is going to be for the total. We have one column for the voltage, one column for the current, and one column for the resistance. And in some cases it helps to do a fourth column for the power. Usually add that on later if you need it, and we will actually end up needing it in this problem, so I'll go ahead and put that column on there now. And we can start listing everything that we know in this chart. So we know the resistances of the 4 bulbs. So we have A is 6 ohms, B is 3 ohms, C is 12 ohms, D is 24 ohms, and the equivalent resistance of the entire circuit is 10 ohms. We also know the voltage of the battery supplying the entire circuit is 24 volts. So, as long as you know two of the 3 things of the V, the I, and the R within a row, you can solve for the last thing. So we can start by getting the current flowing out of the battery, which is the total current in the circuit. So under part C, we can say the I total is equal to the total voltage divided by the total resistance, which we called R equivalent. And that is 24 divided by 10, or 2.4 amps. So I'll put that in the appropriate place in the chart. Then we can start looking at the parts of the circuit. Since A and B are in parallel, that means they have the same voltage across them. And since C and D are in parallel, that means they have the same voltage across them. With the voltage, that voltage that's across A and B, when added to the voltage across C and D, is going to be the total voltage of the circuit, since voltages in series, added together. So let's start by, since we're focusing for part C on bulb B, because it wants the current through point Y, let's focus on the voltage across A and B. So the voltage across A and B is equal to the total current flowing through it. Since the current comes out of the battery, and that current gets split through A and B and then rejoins here. So since we're looking at the total voltage across A and B, we're looking at also that total current as it flows through A and B, times the equivalent resistance of just A and B. So that is, the total current was 2.4 amps times the resistance of A and B combined, which was up here, 2 ohms, and 2.4 times 2 is equal to 4.8 volts. So that's the voltage across resistor A and resistor B. And from that, we can figure out the current through those resistors. Now again, we're only concerned with the current through resistor B, or bulb B, which is the voltage across bulb B divided by the resistance of bulb B. The voltage across bulb B was 4.8 divided by the resistance of bulb B, which is 3, and that's equal to 1.6 amps. So that's the answer to, and I'll go ahead and fill it in the table, of 1.6 amps. And the second thing in part C says to indicate the direction of the current through point Y. So current flows out of the positive terminal of a battery. So if you have the battery here and the positive terminal is up here, the current flows out of the circuit around here to this junction, and at that junction it splits 2 ways. Some of the current flows through A, and some of the current flows through B. So the current going through point Y is flowing to the right. So on the diagram, you can draw an arrow next to the Y showing the current going to the right. So why does the electron flow from Z up to point X? And if you remember, the flow of electrons, because electrons are negative, is in the opposite direction of the conventional current, which is defined as the flow of the positive charge. In part D, calculate the energy dissipated in the 12 ohm bulb in 5 seconds. So, the 12 ohm bulb, right here, we need to get some information to get the energy dissipated, and the energy dissipated depends on the power. So we're going to need to know several things in order to get the power. So let's go ahead and just fill in the remainder of this chart. So the voltage or the current through bulb A can be found just by doing Ohm's law with this voltage and this resistance, and that gives you 0.8 amps. Then you could do a similar technique to what you did here. We got the voltage across A and B. You could also get the voltage across C and D. I'll just put it down here. The voltage across C and D is equal to that total current times the equivalent resistance of just C and D, which is 2.4 amps times 8, and that is equal to 19.2 volts. So I can put that in the table right there and right there, and then I can easily get the current for those last two bulbs by using Ohm's law. I'm going to end up getting the current through bulb C is 1.6 amps, and through bulb A is 0.8 amps. And now we have this whole table filled in, I can go ahead and calculate the power, and I'm just concerned with the power in the 12 ohm bulb C, so just focus on this row of the table, and power is equal to the current times the voltage. So P equals IV, and we're looking at bulb C, so I'll put some subscripts on there. The current through bulb C, or the current through bulb C, is 0.8 times the voltage across, or sorry, that was 1.6 times the voltage across bulb C, which is 19.2, and that is equal to about 30.7 watts. 30.72. So I'll put that in that column. And the energy is equal to power times time. So the energy dissipated in bulb C is equal to the power multiplied by the time, which is 30.72 times 5, which is approximately equal to 154 joules. And for part E, rank the bulbs in order of brightness, with 1 being the brightest. If any bulbs have the same brightness, give them the same ranking. So the brightness of a bulb is determined by its power. You may be able to just eyeball the numbers in this table and just looking at the V and the I to figure out which one is going to have the highest power and go in order from highest to lowest power. C and D have a much higher voltage than A and B, and so if you look at it, you can probably tell that C is going to be the highest power, and then D is going to be the next highest power. I'll go ahead and put the calculations in the table. The power through D is 15.36 watts. So C is the highest, and then it was bulb D. Then after that, it's going to be bulb B, which has 7.68 watts of power. and finally bulb A, which has 3.84 watts of power. And just to make sure everything was done right, the total power in the entire circuit should add up to the total power you obtain just by multiplying the total voltage by the total current. 24 times 2.4 is equal to 57.6 watts, and if you add up these four powers, you'll find that you also get 57.6 watts. It's a good way to just kind of double check the final answer.